the most important fundamental discoveries you can think of in statistics in 19th century. And this is a very interesting theorem, and this is the generalization of this thing Sn, right? Sum of n independent random variables with same mean and variance. Okay, that's what we really want. So what is the central limit theorem saying? Let us quickly summarize. So what is the central limit theorem saying? It says that you have x1, x2, xn as a sequence of independent and identically distributed random variables with mean mu and variance sigma square. Okay, so this is what you have. So mean is mean mu and variance is sigma square, that is given to us. And let us find out the sum Sn of x1 plus x2 plus xn. And obviously what we are interested in, what we are really interested in is that we want to find out what is the distribution or what is the probability density of Sn, the sum of n independent normal random variables. Okay. And this particular statement, the statement of central limit theorem, says that in the limiting condition as n tends to infinity, this mean centered, that means that you subtract the mean of this particular random variable Sn and you normalize it. What is the normalization? You divide by the standard deviation. Sigma root n is the standard deviation, you divide by it. So this new random variable Sn star, which is almost the sum of n independent random variables. So this Sn star, so probability Sn minus n mu divided by sigma n less than or equal to x. So this particular probability is actually the CDF of standard normal. So what we are saying, Sn star is roughly the standard normal distribution. In what sense? In the sense that the cumulative distribution function in the last line, if you see, the cumulative distribution function of Sn star actually matches with that of standard normal density as n tends to infinity. Okay, so that is the understanding. That is what we understood last time, and there were several things that we discussed based on central limit theorem. So I'll quickly recall this central limit theorem again, and we'll see how we actually can use this central limit theorem in computing few things. Okay, so how can computations become easier using central limit theorem? Let us try to understand. Okay, so once again, let us quickly summarize. So x1, x2, xn be a sequence. This be a sequence of IID, independent and identically distributed random variables with mean mu and variance sigma square. Okay, so this is what we have. And we define this Sn to be equal to x1 plus x2 plus xn, the sum of n independent normal random variables. And the question is, so the question that we have always asked is that if you have n independent random variables, then what is the distribution of their sum? The distribution of sum is the question we have been asking for a long time. Every time this is the transformation that we have looked at, we have asked this question, and here also we want to ask this question. The distribution of sum, and what this CLT says, CLT, central limit theorem, implies that limit n tending to 0, probability of Sn minus n mu divided by sigma root n, right? So this particular standard deviation term, sigma into root n. So sigma into root n, that's the standard deviation. This less than or equal to x is equal to phi x. Okay, for every x in R, where phi x is the what is phi x? Phi x is the cumulative distribution function of normal 0, 1, standard normal random variable. Okay, so this is what it is. So we will call this Sn star to be equal to Sn minus n mu divided by sigma into root n, right? So this is the standardized thing. So what we are saying, what we are really saying is the following. So Sn star is approximately going to follow. So approximately going to follow normal 0, 1. And what is the meaning of this approximately going to follow? The meaning of this is that CDF of Sn star approaches to the CDF of normal 0, 1 as this n tends to infinity for every x in R. That is the meaning. Okay. So the meaning of this approximation is this. Okay. So this is what we are saying. This approximately, that's what I have written. The meaning of this particular approximately follows is this. Okay. And if you have this particular thing, then from here, what can you say about Sn? So what is the distribution of Sn? Sn approximately follows which distribution? Follows normal distribution with this mean and this variance, right? So this is the approximate distribution of Sn. So this is the most important thing. And again, what is the meaning of this approximate? So I just have, like, if you have a standard normal random variable by normalizing, so this is the property of normal random variable that I'm using, right? So if x minus mu divided by sigma follows normal 0, 1, then x follows normal mu sigma square, right? So that's the property I'm following here, and using that property I can say something about the sum. So basically x1 plus x2 plus xn approximately follows. So this is something that is really very important. Normal n mu and n sigma square. Okay, so that is really the meaning of central limit theorem. And what is this approximately follows? It means that as n tends to infinity, this x1 plus x2 plus xn, which is equal to Sn, this random variable, the CDF of this random variable actually approaches CDF of this normal n mu sigma square, right? Okay, this is basically the meaning of this approximately follows. Okay, so for us, this is the statement that is really going to be important, right? So the statement that is really going to be important to us is basically this statement. So this is the statement that we will use, or this understanding derived from the statement that previously we have seen. This is what we are really interested in, and this is what we will look at. Okay, so this is something that that is important. That is the central limit theorem. Okay, and as an application of the central limit theorem. Okay, so let us see the first application. Okay, so let x1, x2, xn, okay, this be the sequence of IID Bernoulli P. So what does that mean? X1, X2, Xn is the sequence of IID Bernoulli random variables with probability of success P. So what does that mean? Basically, that means that X1 is equal to Xi is equal to 0 with probability 1 minus P, and this is equal to 1 with probability P, right? So you are doing a coin flip and you get, so suppose this 1 corresponds to heads, then you get heads with probability P, and you get tails with probability 1 minus P, right? So that is what you have. And this is your Bernoulli random variable X is equal to 0 with probability 1 minus P and is equal to 1. So what is the mean? So the mean of each of these Xi, what is the mean of this Bernoulli random variable? What is the mean? Anybody? From here, can you easily tell quickly what is the mean of the random variable?
So it will be P.
Correct. And what is the variance of Xi?
P into 1 minus NPQ.
P into 1 minus P. No, not NPQ. It's just P into 1 minus P, right? So this is what you have. So now what is Sn? Sn is x1 plus x2 plus xn. We already know that this is a binomial density. This is a binomial random variable with NP and NP. Okay, so the two parameters here for binomial are N and P, right? So Sn has this particular distribution. We already know. we have already proved that sum of n independent Bernoulli p random variables is actually a binomial random variable with parameters n and p. But what is central limit theorem saying? CLT. What is CLT saying? CLT implies that Sn minus n times mu, correct? So this is your mu, Sn minus n times mu divided by sigma into root n. This follows normal 0, 1 approximately, right? This is what central limit theorem says. What is central limit theorem saying? Central limit theorem is saying Sn star, which is nothing but Sn minus n mu divided by sigma root n, follows normal random variable with 0, 1 approximately because of this particular statement, right? So this is what central limit theorem is saying. So I can write this statement down, sigma root n. And what is mu and what is sigma here? What is mu and what is sigma here? Can
So
you
mu
tell?
would be p. Sigma is your root of.
Sigma is what? So root of n p 1 minus p. This is what I'll have, right? So this approximately follows normal 0, 1. This is what it is saying. So I already know that Sn follows binomial NP. I already know that Sn follows binomial NP. But what I'm getting from central limit theorem is that this particular random variable Sn minus NP divided by root of NPQ or root of NP1 minus P approximately follows normal 0, 1. And this is what is really going to be of help to us. Okay, so this is what we really are going to look at, and using this we are really going to approximate the binomial probabilities with these standard normal probabilities. Okay, so this is what is going to really help us. So one homework I will like you to give, like you to give is the following. Okay, so what you can actually do is the following. Okay, so you can look at these random variables. So what are we calling these random variables? Sn star, right? So these random variables we are calling Sn star. So I will say S1 star, S2 star, S3 star. They all have they're all discrete random variables, right? They're all discrete random variables. For some of these random variables, say up to S30 star. Okay, they are all discrete random variables. Can you draw the PMF? Okay, it is not easy. For first couple of things you can very quickly draw these PMFs, but after a certain stage you cannot. So what is the formula? So formula is Sn star. So for example, what is S1 star? So S1 star, what will be it equal to? It will be equal to S1 minus P divided by root of P into 1 minus P, right? So S1 is what? S1 is basically X1. S1 is X1. So you are just looking at X1 minus P. So this is nothing but X1 minus P divided by root of P into 1 minus P, right? So this is your random variable, and X1 takes two values, 0 and 1. So based on that, you know what are the values in Z1, and then the probabilities you can calculate. And similarly, you can see how the PMF, probability mass function, really looks like. And I want you to observe that as you go to S star 30, I want you to observe the shape of the PMF. Okay, I want you to observe the shape of the PMF, and you will realize that the shape of the PMF actually almost resembles a bell shape. Okay, so it almost resembles a bell shaped curve. So that is something that you will have to observe, and once you observe, then you will appreciate how this thing is really working very nicely. Okay, so now how will we apply central limit theorem? Okay, so how will we apply central limit theorem here in approximating the probabilities? Let us quickly find out. So if I am interested in calculating this probability, okay, so what is the probability that I want? So let us consider the example. So the example is this. So what is the example? Suppose y is a random variable which follows binomial density with two parameters 20 and half. Okay, so this is binomial with 20 and half. So what am I interested in calculating? I am interested in calculating this probability. So suppose I am interested in calculating this probability. Say probability, one particular example, what is the probability I can take? So this is 20, n is equal to 20, right? So suppose I am interested in calculating probability 8 less than or equal to y less than or equal to 10. So what is the probability 8 less than or equal to y less than or equal to 10? Can anybody tell? How will you calculate directly? Can you use binomial formula here? Obviously, you can use binomial formula because you know that y is a
1/2 for
binomial.
20 into 20C8 plus 20C9 plus 20C10.
1 by?
1/2 for 20
Correct.
into 20C8 plus 20C9 plus 20C10.
This is the probability, right? Correct. Absolutely right. So this is the probability that actually you will have to calculate. And what are you really required to calculate? So many things you are really required to calculate. What are the things that you are calculating here? So what is the most difficult part? The most difficult part is to work with this particular sum of binomial coefficients, and then you have 1 by 2 to the power 20, right? So typically such a calculation you will appreciate as n increases. What is n here? N is this particular thing. As n increases, you'll appreciate that this calculation will become really very tedious because binomial coefficients calculations, our desktops also sometimes after certain limit they will not be able to handle these type of calculations. Okay, so this is something that is important. So now what am I going to do? I am going to take help of central limit theorem. Okay, so what am I going to do? I am going to take help of central limit theorem. So how will I take help of central limit theorem? So I know, notice, what do I know? Notice y is actually equal to x1 plus x2 plus x20. Do you all agree? Y is equal to x1 plus x2 plus x20, where xi follow Bernoulli with probability half, the probability P of success half, and xi's are independent. Do you all agree that this statement is true? We have already seen this.
Yes, sir.
Correct? So we know that binomial is actually sum of n independent Bernoulli random variables. Okay, binomial is sum of n independent Bernoulli random variables. So here we know that what is this expectation of xi. So this is actually equal to S20 for us in our notation here that we have used. This is actually equal to S20, right? So what is the expectation of xi? P, and what is variance of xi is P into 1 minus P, right? So what are these numbers? Can you tell me what are these numbers? So this is equal to half and this is equal to half into half, which is equal to 1 by 4. Is that okay? Is that okay? Fantastic. So
Yes.
I have these numbers. And now what is
Yes,
n
sir.
here? What is n here for me? N is equal to 20. N is equal to 20. Excellent. So what is CLT telling? CLT is telling that probably CLT is saying that Sn star, which is nothing but Sn minus n mu divided by sigma into root n, follows approximately which random variable? Normal 0, 1. That is what central limit theorem is saying. Do you all agree? This is the central limit theorem. And now we have all the information that we want, right? So this is my mu, this is my sigma square. So if I have all this information, if I substitute this, what will I get? So let us see what will I get. So the probability that I am interested in calculating, is 8 less than or equal to y less than or equal to 10. Okay. So this basically I can write down this probability as 8 minus n mu divided by sigma root n less than or equal to y minus n mu divided by sigma root n less than or equal to 8 plus n mu divided by sigma root n. Can I say that?
Yes, sir.
Is that okay?
10 minus
Hi.
10 minus n.
Yes. Sorry, did I make a mistake? 8 minus.
That will be
10
10 minus n mu, not 8 plus n mu
Yes, sir.
on the right side.
It will be 10 minus n mu divided by sigma. Is that okay?
Yes, sir.
Yes.
Yeah. So I am going to do this. So when I'm going to do this, what will I get further? So what is n mu here? What is n mu here?
10.
10.
N mu is 10. What is sigma root n here?
Root 5.
It is root 5, correct? Less than or equal to, what is this random variable sitting over here? I have this as my Sn star, right? So this is my Sn star, and 10 minus 10, so it will be 0 here. So you'll have a 0 here, right? And now here, what I can write down? I can write down this is roughly equal to phi 0 minus phi of minus 2 by root 5. Is that okay? Can I write this? Can I write this thing down? And why this approximately equal to? This approximately equal to, where is it coming from? It is coming from central limit theorem. Is this step clear to all of you? This is
Yes,
something that is really very important. This step is a key step here. So this equality is fine up to this step because I have not changed anything. But this equality will turn to approximate equality, and this approximation phi 0 minus phi of minus root 2 by 5. Is that okay?
Yes, sir.
Yes, sir.
And what is this probability? Can you calculate? Is that okay? Can you just check? Abhinandan, can you please mute yourself, Abhinandan? Yeah, thank you. So do you get this as 0.31 roughly? Can anybody quickly check? And can some of you actually calculate this? I think this turns out to be 0.46. Exact calculation if you do, roughly it is 0.46. Can you just check it once?
Zero 0.457.
457. Okay, so 0.457. And what is this value? Is it 0.31 roughly? Is it okay? So this approximation, though is nice, it doesn't really like theoretically what is really happening. It is not really matching very well, right? So this value 0.457 is not really matching well with this value, which is 0.31. Okay, so why that has happened? Because we have been looking at PDFs and we have not been looking at CDFs, and roughly converges to, okay, so roughly converges to, roughly approximately equal to, the meaning is that CDF of Sn star is approaching CDF of normal 01. Okay, so let us see what is really happening here. Okay, so we'll have to do a slight modification here, and once we do this slight modification, then we'll be through. Okay, so for example, this is a rough sketch. Okay, this is a rough sketch. But suppose I have this particular thing. Okay, comparison of binomial NP with Sn. Huh? I am doing it with Sn, not Sn star. Please remember this. So Sn is a normal random variable, and approximately, okay, Sn is a normal random variable, and this binomial NP is this binomial NP. So this, in our notation, actually we are calling it as Sn, and I will look at the normal random variable with NP and NP1 minus P. Okay, so this is the normal random variable I'll look at. So I don't want to do mean centering, that's why I'm doing this. Okay, so 0, 1, 2, 3, 4, 5, okay, 6, so on and so forth, up to n. So this is the support of this binomial NP, right? Discrete random variable. And how would the PMF look like? So the PMF will look like this. Okay, so there will be some values. These are the probability values that you will see, and this will finally be n, something like this, right? So this is how the probability values PMF of this will look like. And if I look at this particular density, then this particular density will roughly look like this. Okay, this is how this density looks like. And now if I'm interested in calculating the probability of Sn is equal to 4, okay, if I'm interested in calculating the probability of Sn is equal to 4, what I am doing really, if I want to approximate it, then what I am really going to look at is I'm going to look at this small interval. Okay, so this interval I will call 4 minus half to 4 plus half, and I will look at this particular area, shaded area. I will look at this particular shaded area, and this particular shaded area that I have, I'll pick that shaded area and I'll say that this shaded area is actually the approximation of the red line that is standing there, right? Which is nothing but the true value that I'm really interested in doing. So rather than looking, so if I 8 minus 10 divided by root 5, what I am really doing is that I am really excluding this 8 and 10. I am really excluding this 8 and 10 in this particular thing, right? I don't want to exclude because I have a discrete random variable here. The discrete random variable will have probability mass, which in the probability density function you will ignore, because at a particular point probability density, the probability value is 0. So that's the problem that is happening. And when you have a discrete random variable, what typically we will do is that we will look at, instead of 8, we'll look at 7.5, and instead of 10, we'll look at 10.5. Okay, so if I do that, then what will happen? Can you please check? So instead of that, so this approximation is called as continuity correction. Okay, so this particular thing is called as continuity correction, because I am approximating a discrete random variable with a continuous random variable. So this continuity correction needs to be done. So I look at this continuity correction, and using that continuity correction, what I will have is probability 8 less than or equal to y less than or equal to 10. This probability is same as probability 7.5 less than or 7.5 less than or equal to x, less than or equal to y less than or equal to 10.5. This does not change as far as discrete random variable is concerned, right? So this probability is again 7.5 minus n mu, which was 10. So 7.5 minus n mu divided by sigma root n less than or equal to y minus n mu divided by sigma root n less than or equal to 10.5 minus n mu divided by sigma root n. Okay, so this is what you will have, and this will be equal to phi of, now if you see 0.5 divided by root 5 minus phi of, now you'll have minus 2.5 divided by root 5, right? So this is what you will get, and this approximation comes from CLT. Okay, this approximation comes from CLT, and this value, now you calculate, it will turn out to be 0.4567, and this value, which is 0.4567, this value is very close to this particular value 456 that you had exact calculation. Okay, so this continuity correction is really very important. And once you do this continuity correction, then your answers will be correct, right? So this continuity correction I'll just write down. So this continuity correction I'll just write down theoretically. So what is this continuity correction? So the continuity correction that you will have is the following. Okay, so if Sn is so f Sn x, right? So f Sn x is, if you want to calculate this probability, then this will be equal to phi of x plus half minus n mu divided by sigma root n minus phi of x minus half minus n mu divided by sigma root, right? So this is the continuity correction that you will have. This is the continuity correction that you will have. And using this continuity correction, you will actually compute the probabilities. Okay, and if you want to compute this probability, then what you should do using continuity correction, you should calculate x plus half minus n mu divided by sigma root n, right? So you have to go half step further, a little bit further. Okay, you have to go a little bit further, and when you go a little bit further, you are actually accounting for that probability mass. That's the continuity correction that you will have to do. So I hope this thing is clear to all of you. And I hope you can use this central limit theorem idea to actually calculate approximate probabilities in case of binomial. So when you see a binomial random variable and when you want to compute binomial random probabilities, binomial random variable probabilities, especially when n is greater than or equal to 20, you can very safely use this binomial normal approximation to binomial probabilities, and using this you can actually calculate the probabilities. Okay, so this thing is really very important. So is this okay?
Excuse me,
Yes,
sir.
sir.
Yeah. Okay.
Sir,
Yeah. Yes, Piyush.
Sir, can you please again explain, sir, this continuity correction?
So this continuity correction is, see, if you want to calculate what really happens is the following, right? So if you are interested in so this is a normal random variable I have here, right? So what I have here is a normal random variable, and in this normal random variable, I really do not care what is the probability at the point x is equal to 4, because for a continuous random variable, probability at a particular point is 0. Is that correct, Piyush?
Yes, sir. Yes, sir.
So if I calculate value, if I calculate value of cumulative distribution function at the point 4, I am really looking at this particular area. You just see if you can agree. I am calculating this particular area. Is that okay? If I
Yes, sir.
calculate CDF value at 4, I am calculating this particular area. So as far as the discrete random variable is concerned, the probabilities that I am really giving importance to are actually these probabilities which I have encircled here. I was interested in having probability at x is equal to 4 also included in this, but because of the continuity correction, because of this continuous nature of approximation, I really don't care what happens at 4. Do you agree?
Yes, sir.
So I'm kind of ignoring the probability at 4 by looking at CDF value at 4. So had I looked at CDF value at 4.5 here, then what would have happened? Then what would have happened is I would have really looked at this particular point. I would have added this much of area in continuous random variable, correct? But then for the discrete case, I would have roughly approximated accounted for this particular part also, and my approximation of the probability would be accurate. Do you understand this part?
Yes, sir.
But so by instead of so if I'm interested in looking at probability of random variable less than or equal to 4, if that is what I am really interested in looking at, then what should I compute? Then what should I really compute is less than or equal to 4.5. For a discrete random variable, does that make sense? Does that make any change? No, it does not make change for the discrete random variable. But for continuous random variable, what happens? You are going little bit to the right of 4, and as the approximation takes place, you are accounting for the probability at x is equal to 4 also. Is that clear what I'm trying to say?
Yes, sir.
Yeah, so that is what I have done in the that is what I have done. So if you want to calculate probability of the binomial random variable at small x, so the small x is 8, for example. If you want to calculate the binomial random variable, x takes value 8. I took 8 less than equal to y less than equal to 10. You could have just taken y is equal to 8. I am interested in calculating this probability y is equal to 8. So this is what I will have. So x will have value 8. So how will I calculate the probability? The way I will calculate the probability is that I will calculate the probability at 8 plus 0.5 and 8 minus 0.5. So this is what I'll calculate. So I will look at 8 plus 0.5 and 8 minus 0.5. Is that okay? Does that make sense to you?
Yes, sir.
That's what I have done. And in order to calculate those normal probabilities, I have to do normalization. So that normalization by subtracting mean or dividing by standard deviation is done anyway to convert to normal 0-1 probabilities. And this is what I'm going to calculate. Is that okay?
Yes, sir. Thank you, sir.
So that is what I have done. And the same logic, Sn less than or equal to x, you can have. So x plus half. Okay, you will do x plus half. So these are the formulae that you have to remember. Once you remember this formulae, once you understand this formula of continuity correction, this binomial probability calculations is not really a difficult task. Is that okay? Excellent. So now, if this part is clear, I want you to show you something which is really very interesting. Okay, so this intuition is there. How this intuition really actually comes into play. I want to share something. Okay, so let me share other screen. So, okay, so I believe my screen is visible once again.
Yes, sir.
And can you see this YouTube thing? Let it load. Oh, what happened? The screen is visible now or no? I think
sir,
it's
it's
gone,
not
right?
visible.
It's not visible. Let me share once again. Okay, so let me see. Let me try once again. Okay, so now you see the YouTube video that I'm going to show. Okay, so this particular thing that you see here, this particular thing is called as Galton board. Okay, so Galton was a scientist basically, and this guy Galton was first cousin of Darwin. Okay, so Darwin, I hope you all know who proposed this theory of evolution, right? So Darwin's first cousin. Okay, so this guy Galton. So this guy proposed this. So there is a Royal Society in London, so where people actually used to present their discoveries in earlier days, and a replica of this particular device that you see here. So this is called as Galton board. Like a primitive replica of this particular thing that you see here was actually demonstrated by this guy Galton in this Royal Society meeting in London in something in 1880 or 1885, 90, something during that time, 1880s. Okay, in one of the meetings he actually showed this, and what he showed is this. Okay, so you see what this is. Okay, so let's see the video. Now you see what is going to happen. So now you observe carefully. Okay. Are you all able to see what is happening in this video? Are you able to see?
No,
Yes.
it's not.
Okay, so once again, now I think it will be zoomed in a slow motion. Can you see what is happening?
Yes, sir.
So from the top, what has happened? From the top, there are ball bearings that have been dropped. Okay. And you see at this level, there are several levels. Okay. And each of this level, there are certain slots. I'm pointing them. So you might be able to see these slots here. Can you see the slots here? All these slots. What
Yes, sir.
happens? The ball bearing comes at this slot, it hits the slot, and randomly it goes either to the right or to the left. Okay, that's what is happening. Then it comes here, then again the same thing happens. I suppose the ball bearing comes here first, then either it goes to left or right. Suppose it goes to left, then it comes here, then again here it either goes to left or right. So either it goes here or it goes here. So it goes here, then here, then here, then here, it keeps on doing. And after this, it falls down. Okay, so once it comes at this level, then it falls down through one of these channels. Okay, and then it is collected at the down. And what is the most surprising thing happening here? You see what is the most surprising thing happening here? Once again, you see. Okay, let me play this again. So once again, you see what is happening. So these ball bearings, when you put them through, each of them will go down. And eventually, what shape do you get at the bottom?
It's roughly
Normal distribution.
normal
It's
distribution.
roughly normal distribution. And why do you think is this happening?
So we can consider each pellet to be a separate event with like um, the identical individual events.
Correct. So what is it?
There's just n binomial events like happening together. N
Bernoulli,
Bernoulli events happen.
Bernoulli events, right? So what is the Bernoulli
Yeah,
event? The Bernoulli event is
it's the moving of left or right when it hits a
correct,
particular spot.
correct, absolutely right. And then what is happening? Then what is happening? Why you see a normal density then? Why you see a normal
Because
density?
number of balls is very high.
Correct. So
That's
number
why
of balls is very high. Then
it converges in the center point. Like a
correct.
normal
So using
distribution.
central limit theorem. So it's the application of central limit theorem, right? So using central limit theorem, you can see this thing is actually converging to the normal density. So this is something that was a very interesting discovery made in 1880s. And this was shown by this person called as Galton. And this Galton is like first cousin of Darwin. Okay, Charles Darwin. So he actually demonstrated this, and now you can see this pictorial demonstration, pictorial representation of this thing. So unfortunately, you have not been to the campus yet, but when you come to the campus, in the campus there is a science exhibition called as Hazley Science Exhibition in that main building. Okay, and in that main building there is an exhibit there, which is this Galton board, and you can actually go there, spend some time, and you see how these pallets or ball bearings, go down one by one through each slot, and how every time you get this normal random variable, right? So what is the most important thing that you observe here is that each of these xi's, each of these random variables x1, x2, xn, okay, at their level, individual level, x1, x2, xn, the motion of x1, x2, xn is really random, right? Either it can go to right or left, right or left, right or left. So each individual xi level, the motion is random, but collectively, for suppose there were 1000 pallets which were falling down, then collectively for those 1000 pallets, x1 plus x2 plus x100, independent and identically distributed, you were able to exactly tell what will happen when they fall down. They will form a normal density, right? So collectively, how is that motion really going to work, as opposed to looking at them individually, is something that this experiment can demonstrate. Of course, Galton was interested in showing this for something else. Um, he wanted to talk about, you know, how certain properties are passed on hereditarily, like, you know, the brilliance and, you know, things like that. He was more interested in that. But like that part of his discovery actually failed, but he hit on to something which is called as regression on means. Okay, so that is one of the most important topics that we learn even today in our standard stats regression courses. Okay, so this is one of the most important things, that part of history and how he was able to demonstrate like in real life this central limit theorem and all those things. It's a wonderful piece of history. I think you should really read. It's called as Galton board. Okay, so you look at this Galton board, you look at the videos in YouTube about this Galton board and different explanations about how these Galton boards really are used. Okay, so I will encourage you to look at these particular things. Okay, let us see a few more applications of this central limit theorem. Okay, so let us see a few more examples of this central limit theorem. Okay, so a bank teller serves customers standing in queue one by one. Okay, the service time xi for each customer I has mean and variance is equal to 1. Okay, assuming that the serving times for different customers are independent, and letting y to be the total time bank teller spends. Serving 50 customers find this probability 90 less than y less than 100. So how will you approach this problem? Okay, and I want 90 less than y less than 110. Okay, it doesn't matter, but for symmetry I want 110. So how will you approach this problem? What will you do?
So, since n is sufficiently large at 50,
Correct.
we can more or less assume that it is kind of the standard normal distribution.
Correct.
After you transform it.
Correct.
So it will be
so the first thing that we have to look at here is the following. So when do you apply central limit theorem? You can apply central limit theorem only when you have sum of n independent random variables with same mean and variance. Do you agree? So you have to make sure that y actually is sum of n independent random variables, right? So that is clear. What is clear? Y, the serving time for 50 people by the bank teller, is actually sum of x1 plus x2 plus x3 plus x50. First, do you all agree that this is what is there? First, do you all agree? And these xi's are independent. Why are they independent? They are all independent because assuming serving time for different customers are independent. That is the assumption that we have made. So all these xi's are independent. They all have same mean. What is the mean? So expectation of xi is equal to 2 and variance of xi is equal to 1 and xi's are independent. So if all these conditions are satisfied, then what will we do? If all these conditions are satisfied, then what will we do? We can apply central limit theorem, right? So how will we apply central limit theorem? So what is the probability? So the required probability. What is the required probability? The required probability is probability 90 less than y less than 110, right? So this is basically same as 90 minus n mu divided by sigma root n less than or equal to y minus n mu divided by sigma root n less than or equal to 110 minus n mu divided by sigma root n. So we have all the values here. This is my mu, this is my sigma square, n is equal to 50, right? All these values are available with me. And what is y? So y is this sum. In my language, in the notation that we have used, it was Sn, right? So this particular random variable becomes Sn star. So what are the values? So do you all agree this is 90 minus n mu? So n is 50, mu is 2. So you'll have 100 here and divided by sigma is 1 root n. So root n is 50, root 50 less than or equal to Sn star in our notation is less than or equal to 110 minus 100 divided by root 50. So this I can say is approximately equal to, where this approximately equal to comes from central limit theorem. So this is approximately equal to probability. So phi of 100, so 10 divided by root 50 minus phi of minus 10 divided by root 50. Is that correct? So this is equal to phi of, I think it will be phi will come out. So is it minus root, sorry, root 2 minus phi of root 2 minus, is that correct? Phi of minus root, is this calculation correct?
Yes, sir.
Yes, sir.
25, 5 to 2 by root 2 root 2. Yeah, this is right. So this is what you have. So this is the calculation you will do. And what is this probability? Whatever it comes out to be.
0.86.
0.886.
So actually it's 86 if you take the like 10.5 to minus 10.5.
No, we'll not take 10.5 here. Why will we not take 10.5?
Because it does not include 90 and 110.
But the time required to serve, is it a discrete random variable or continuous random variable?
It will be continuous.
So if it is a continuous random variable, then we do not need
Then there is
continuity
no-
correction.
Yes, sir.
When you are approximating a discrete random variable by a continuous random variable using central limit theorem, in that particular case, you will require continuity correction. But if you have a continuous random variable and you are approximating a continuous random variable with normal 0, 1, another continuous random variable, you do not require continuity correction. Okay, so I have not used continuity correction. So I think then that value is not 86. I think it will be 84, 85, something like that. I don't know what is the value. 84. Okay, 0.842. So that's the value that you will get in this particular case. Okay. So this is how actually you apply central limit theorem. Okay. So this is how you actually apply central limit theorem. Any doubt about what we have done so far today? Is this part clear?
Yes, sir.
Okay, so if this part is clear, if approximating this probabilities, this part is clear to you, then there is one more approximation I wanted to say today, but now we do not have enough time, so I'll not say it today. We'll do it in tomorrow's class. So it's a very simple thing. It will take only 5 minutes actually, but anyway, I'll not do it today. We'll do it tomorrow. It's called as Poisson approximation to this binomial probabilities. Okay, so you can approximate this binomial probabilities by Poisson probabilities also. Today we saw how we approximate them using normal density using central limit theorem. And once that approximation part, only for completeness sake, I'll talk about it for 5 minutes tomorrow. And once that part is over, then we'll move into the next part, which is statistics and sampling distributions, and something which we had been talking about previously. So for example, if you remember in the first class or in the first week of this course, we were talking about, not knowing what is the probability of success when you not knowing what is the probability of heads when you toss a fair coin. So how will we guess, or how will we estimate, so to speak, that probability of obtaining heads for a given coin? And you remember some of you had said something about tossing a coin several times and look at the ratios and things like that. I hope you remember that discussion. Okay, so we are going to come back to that discussion tomorrow, and we are going to formalize it, and we are going to understand few more things about estimators, for example, taking motivation from that discussion. Okay, so from tomorrow's class, we'll mainly focus on to the statistics part, like when data is given, how do you do certain computations, and what are the things that you are required to know. Okay, so in that we will be talking about three important distributions which will help us analyze things. So those distributions will be chi-square distribution, t distribution, and f distribution. And I will actually derive the PDF of T and F distribution using certain transformations. So the transformations is something that I had discussed in the class, and in the proof of deriving T and F, you will see the real power of using those transformations. Okay, so I will do that part in probably tomorrow's class and next week, and we'll try to understand how we can analyze like certain things, how we can estimate certain things, how we can quantify if one estimate or one guess is better than the other guess, and so on and so forth. So these are the type of things we really want to understand. So we'll try to do that part from tomorrow's class onwards. Okay, so this is about central limit theorem, and after that, one particular small thing about how I can approximate binomial probabilities using Poisson probabilities. We'll move on to that data part. Okay, so statistics part. So that's what we plan to do in subsequent classes. So we'll stop here today. We'll meet tomorrow, and we'll continue our discussion in tomorrow's class. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So I'll definitely encourage you to go and see those few videos related to this Galton board, and try to understand this concept of central limit theorem like in more details. Okay, if you have any other things to discuss about it, we can always discuss about these things. But I really want you to look at these type of videos on YouTube and see. Thank you. See you tomorrow.
Hello, sir.
Ayush.
Yes, sir. Yes, sir.
1 minute. I'm just seeing the mail. Yeah, for this, I think there was standard solution circulated, na? This problem that you are showing.
Yes, sir.
For this, there was. Did I not share that standard solution with you? Like,
Sir,
what
no,
was the
sir.
solution?
Sir, I have a doubt, sir. Like I have written in the mail also. Sir, my method was that I will select 3 coupons, and then if my first and third coupon are even, or first and third coupons are odd, then I'll get an AP.
I think there was some correction done to this solution.
Sir, my marks don't reflect that.
I don't know if your answer is correct using this method or not, but there was some correction done. Let me see and I'll tell you. I
Sir,
remember that because of this particular thing,